Hello everyone, my name is Sarvo Teimuri and I'm a postdoc research fellow at the University of Melbourne. This presentation is about the paper entitled Business Process Variance Analysis based on mutual fingerprints of event log. So I start this presentation by defining what a business process is. As you can see, it is a collection of linked tasks that finds their end in delivering a service or product to a customer. Indeed, a process model defines an order execution among the activities. The execution of a process model is recorded in an event log. Indeed, it contains a set of traces or cases which show a particular execution of business process. As you can see, a trace might have various features. However, the most important three are activity, completion time, and case ID. A process variant is a group of process execution that share at least one attribute. For example, one can create variants based on city, sex, product, or defining some level of SLA and group traces accordingly. Process mining is a young and fast-growing area that embodies a set of techniques for analyzing event logs to extract useful insights to improve process models. Broadly speaking, the techniques can be classified into four groups, as you can see in this slide. So more concrete, process variance analysis technique allows one to compare process variance of the same process model to both quantify and qualify the differences. In general, process variance analysis can be done in two perspectives, i.e. control flow and performance. The former, one tries to understand the existing difference among the activities control flow, whereas in the latter, performance attributes are compared. For example, one can compare the duration time of an activity in each variant to understand which one is slower. Several works has been proposed for process variance analysis. As you see, the most recent ones are here. Some of this work examine both perspectives. However, for the sake of simplicity, they are divided into categories. The work by Van Beest discovers an event structure for each variant and then compute the difference between them and present differences via textual explanation. Cordes et al. Discovered two process models and find their differences. This work is extended by the next author via annotating transition system. Bolt et al. Use process maps to address control flow differences and uses decision tree induction for performance analysis. The last work in this category is similar to the previous work, but it proposed differential graph as well as considering a sliding window to compare control flows over the time. The work in performance perspective proposed some visualization techniques for performance examination. Since our work is very close to the indicated works, we consider them as baselines. All the previous works rely on counting the frequency of each activity and its direct relation to the other activities. This gives rise to a directly follows graph. For example, the following directly follows graphs show the control flow for patients with sepsis infection. One for age older and equal to 70, and the other one for younger and equal to 35. Obviously, there is no clear control flow from the beginning to end in each process variant. So one can set a frequency threshold, though missing some information, still no clear control flow from the beginning to end can be obtained. Even if a clear control flow can be obtained in this way, we don't know whether it has obtained based on chance or no. Indeed, the main question is, if someone else runs the process for each variant several times, would it give rise to the same process, to the same control flow? In this work, we introduce a novel approach that is statistically sound in both perspectives, i.e. control flow and performance. We present a novel graph representation, namely mutual fingerprint, that shows the actual control flow from the beginning to the end in each process variant. This representation cannot be obtained by playing frequencies of events or arcs. Also, it can be annotated with other performance attributes. The followings are mutual fingerprints for the sepsis variants, and one can see easily a clear difference between control flows. In the rest of this presentation, first I give the required preliminaries and then the details of computing mutual fingerprints will be provided. So an event is a tuple of entities with various attributes including activity name, completion time, etc. A trace is a sequence of events, and an event loop is a set of traces. A process variant is a set of traces where they share at least one attribute with each other. A vector is a column array of elements, and if a set of vectors is closed over multiplication and addition operators, it is called a vector space. The smallest of such set is called basis vectors. It must be noted that in Rn there are infinite number of basis vectors. Hard basis vectors are one of the most important basis vectors in Rn. And for analyzing sequential data. So the following recurrent formula provides the hard basis matrix for a given dimension. For the details of this formula, please read the paper. However, at the bottom of this slide, you see some example of hard basis vectors. So the columns of Hn are called wavelet. It is because each column is a wave-like oscillation with an amplitude that begins at 0, increases, and then decreases back to 0, as you can see at the right part of the slide. This is why Haar matrix is also called discrete wavelet matrix or discrete wavelet transformation or DWT. A time series is a sequence of observation on a variable taken at discrete time intervals. A time series can be shown as a vector in Rn. Also, any vector in Rn can be mapped into a hard vector space using simple transformation, as you can see here. The resulted vector, i.e. W, shows the wavelet coefficients. In other words, the combination of wavelets with these coefficients make the initial vector. Wavelet coefficients are not just numbers. They provide interesting meaning, as it shows the variation of inputs value at different resolution. So for example, consider this time series. So W1 shows the overall average of the inputs value. And if we split the input time series into half parts, the second coefficient, or W2, shows the difference between the average of the first and the second parts. Thus, in a recursive way, wavelet coefficients captures all the variations in inputs values. So the purpose framework has 3 parts. In feature generation, so it has 3 parts: feature generation, feature selection, and filtering. In feature generation, we propose a novel lossless encoding where each event is mapped into a numerical vector using DWT. Next, from the generated features, we select those that discriminate process variance and are statistically significant. Finally, we filter those traces that do not carry any discriminant feature, and mutual fingerprints are created based on the remaining traces. Our feature generation has 3-step insights: binarization, vectorization, and vector stacking. In binarization, given an input trace and the alphabet, a binary time series is generated for each event. It must be noted that binarization keeps both the frequency and the location of an event in the input trace. For example, for a trace like E1, E2, E1, E1, and the set of alphabet E1, E2, E3, binarization generates 3 time series, as you can see from the picture at the bottom of this slide. Note that the last time series is a 0 vector because the input trace does not have E3 inside. In vectorization, for each binary time series, the corresponding wavelet coefficients are computed. But why do we need wavelet coefficients and not working with binary time series, as both are kind of vectors? The reason is a time series has 2 characteristics that are called autocorrelation and cross-correlation. The former happens when the value of a time series is correlated with the past values. In process mining, it happens when there are loops or nested loops in the process model. The latter, or cross-correlation, happens when the value of a time series is correlated with the past or future values of another time series. In the process mining, it is common that firing one activity might trigger other activities in the process model. So binary time series have cross and autocorrelation with each other. These properties pose a big challenge in analyzing sequential data. However, DWT embeds this information into wavelet coefficients where one can recover them completely. So just using with the matrix operation. Therefore, working with wavelet coefficient is not only solve the autocorrelation and cross-correlation issues, but also save important information in the input data. For a given binary time series, we just need to compute the inverse of a Haar matrix once and compute the corresponding wavelet coefficients. And we can work with them as a proxy of the input data without losing any information. So when the wavelet coefficients are computed for each event, they can be stacked up into a longer vector that shows a numerical representation of the input data. Next, we can create a design matrix D, where each row is related to each trace and columns are corresponding to the wavelets. After creating the design matrix for each process variance, the most important question is which feature or set of features discriminate process variance. We tackle this problem by proposing a wrapper feature selection method. Wrappers are feature selection techniques that employ a classifier to select informative features. First, we create an augmented matrix X with two labels that denote the process variance. We can divide this matrix into the training and the test set accordingly. In this notation, S shows a subset of features. We say that a set of features is discriminatory if a person trains a classifier with it, the model provides acceptable performance on a test data according to some criteria. Since the proportion of the class labels might be imbalanced for each event or a set of features, F1 score is a good performance metric measure. However, it considers only the true positive instances. In our situation, although classes are imbalanced, but they are of the same importance. Thus, we propose weighted F1 score as defined, as you can see here, where F11 and F12 are F1 scores for each class, and the gammas show the class proportion for each class proportion that varies for different subset of features. For example, if we have the following toy test data, then for E1, the four leftmost columns, gamma 1 is 2 to 3 and the gamma 2 is 1 to 3. These numbers are different if we consider E3 the right most four column. So gamma for E3 is 1 to 2 for both gamma 1 and gamma 2. So these parameters are dynamically adjusted during the testing. So what is a good set of features? For a given set of features, the worst performance of a classifier happens when, after training, it is unable to distinguish process variance or classes. More compactly, it would assign a single label to all of them. Thus, the worst performance will be a weighted value, as you can see here, when if the weighted value when it assigns the test instances into the class 1 or class 2. It takes place when, in detail, it takes place when there is not information in the training set of selected features for the classifier to discriminate classes. So any performance above this value, above this number, show that the trained model is able to distinguish process variance. However, it might be happen by chance. So to eliminate this effect, we resort to the cross-validation to take a sample of performance values, and if the average of the sample is greater than the worst case performance with, let's say, 95% significance level, then we consider the selected features as discriminatory ones. So the last part is filtering. Indeed, identifying discriminatory events, though statistically significant, does not provide enough insight for the analyst to understand the existing differences. Thus, one can create a directly follow graph for each process variant by only considering those traces that carry information about the discriminatory parts. Technically, assume that an edge like EIEJ is found to be the discriminatory feature between two process variants. Then all traces containing this edge are kept. A mutual fingerprint is a directly followed graph created based on this set of traces for each process variant separately. So in the evaluation, we examine the proposed approach in the following machines. So Python 2.7 and the Intel Core i7, 16 GB of RAM, and the Microsoft Windows 10. We used 4 real datasets that are publicly available. So road traffic fine management event log shows the execution of the traffic fine management process at an Italian municipality. For this dataset, we created 2 variants for the fine amount, one for value equal and greater than 50 euros, and the other one for value less than 50 euros. Sepsis event log contains the flow of activities that patients with sepsis disease must follow when they are admitted to a hospital. We created 2 process variants based on the patient's age, i.e. equal and older than 70 and equal and less than 35. For BPI 13, we created 2 variants for 2 organizations, A2 and C. We selected these 2 organizations to have a common ground for comparison with the baselines. For BPI 15, process variants are created based on 2 municipalities, so municipality 1 and municipality 2. Also, for each process variance, we can see various statistics, such as the number of cases, and the mean, max, and average of the traces, and the number of events. We proposed 2 general research questions for each dataset and the corresponding variance. One is about the control flow, and the other one is about the performance. The first research question is, what are the key differences in the control flow of the 2 process variants? The second research question is, what are the key differences in the activity duration of the 2 performance variants? To answer these questions, we consider consecutive events or arcs in directly followed graphs in each process variance and would like to know which ones are discriminatory. For the first data set, so road traffic fine management event log, the following shows the directly followed graph for each variant. Obviously, there is no clear pattern from the beginning to the end of the process that distinguish these variants. However, the approach in this work found 3 arcs that distinguish process variants, as you can see at the bottom of this slide. Since they are not very informative to the end user, we plotted the mutual fingerprints as well. You see a clear control flow patterns in each process variant. To be more concrete, the red arcs are those that we found them as discriminative features. If it is dashed, then the duration time of that arc is also statistically significant between process variants. The right graph shows, so this mutual fingerprint, this fingerprint, show that for a sample of people receiving a fine amount less than 50 euros, the dominant control flow is the one that we discovered. In other words, if we change the sample of the people, given that there is no drift, the actual control flow wouldn't change. Also, pay attention that these mutual fingerprints cannot be obtained by setting a threshold on arcs, on frequency of arcs of the initial directly follows graph. So this slide shows the result of one of the baselines for the road traffic fine management process variants. As you can see, there is no clear control flow pattern from the beginning to the end of the process model. Of course, one can play with the frequency of arcs to remove infrequent arcs, but it does not provide much insight into the actual underlying control flow. And at the same time, we miss some information by removing infrequent arcs. For the sepsis event log, the following shows the directly follows graph for each variant. Again, there is no clear pattern from the beginning to the end of each process that can distinguish these variants. For this variance, the approach in this work found 1 arc that distinguished process variant control flow. In this case, although the discovered mutual fingerprints are similar, one sees a clear difference between the control flows, i.e. Control flow for patients with sepsis disease 35 or younger are statistically different from the same patients who are 70 or older. So for the BPI 13, so you see the directly follows graph for organization A, 2, and C. Again, there is no clear control pattern from the beginning to the end of the process that can distinguish this variance. We found the following mutual fingerprints. You can see that they are the same except that in A2 there is one more arc from completed task to the queued task. So for the last data set, so BPI 15, process variance of, you see the directly follows graph for municipality 1 and municipality 2 of BPI 15. And you see these directly follows graph are very, very noisy. Our approach also, it can discover two mutual fingerprints. You can see, as you can see, one of them is still very noisy. The blue circle in the middle of the right picture shows where the discriminant arcs are located. Indeed, it is an interesting issue for us to see such noisy mutual fingerprints. After a detailed investigation, we realized that most of the traces in the municipality 2 share at least one discriminative feature. Therefore, the filtering mechanism keeps almost all the initial traces. And this is why at the end we have a very, let's say, noisy mutual fingerprint. So I'm going to close this presentation by mentioning the conclusion, the future work. We presented a novel approach for process variance analysis based on discrete wavelet transformation that is statistically sound in both perspectives, i.e. control flow and performance. We introduced the concept of mutual fingerprint that gives insight into the actual process model in each process variant. This approach has separate parts internally that each has its own novelty, such as feature generation and feature selection. Although the proposed approach theoretically works for any dataset, sometimes it might come up with not clear mutual fingerprints. Indeed, this fact takes us to the future work. So the future work can be divided broadly into two parts. On the one hand, one can fundamentally investigate other encoding techniques such as other wavelets family or mixing the current approach with deep learning models to learn a better representation of the input traces. Also, one can propose another feature selection mechanism that is less sensitive to the noise. On the other hand, one can easily apply the presented technique to the other process mining applications such as conformance checking, process discovery, predictive monitoring, and outcome prediction. So thank you very much for your attention.